All right, welcome to the Explainer. Today, we're going to tackle a question that sounds super simple but has a really complex answer. What does it actually mean for something to be pure? I mean, think about it, right? You see the word pure slapped on everything: juice cartons, salt, especially milk. And we just kind of assume it means, no weird stuff added or it's all natural. But if you ask a scientist, that glass of milk in your fridge, yeah, it's not even close to being pure. And that's really the heart of the matter. See, in our everyday lives, pure just means clean or natural. But for a scientist, purity is all about its chemical makeup. It has to consist of only one single type of particle. Anything else, and it's not pure. So that milk we were talking about, it's really a mixture, a jumble of water, fats, proteins, you name it. So let's really dig into that scientific definition. Because once you start looking at the world like a chemist does, you'll see that pretty much everything is way more complex than it first appears. Okay, so here's the rule, scientifically speaking. For something to be a pure substance, every single little particle has to be chemically identical, like perfectly the same. Think about pure sugar or sodium chloride, that's just table salt. Down at the molecular level, it's all the same stuff, totally uniform. And this one definition kind of changes everything. When you look around, you start to realize that almost nothing is a single pure substance. The air you're breathing right now, the ground you're standing on, the ocean, all of it, they're all what we call mixtures, just different pure substances all mixed together. Okay, so if the world is basically one big collection of mixtures, how do we even begin to sort them out? Well, it turns out there's a pretty straightforward way to split them into two main categories. So what exactly is a mixture? It's just what happens when you physically combine pure substances. And that word physically is super important. Like if you mix salt and pepper, they don't magically become a new thing, right? They're just salt and pepper in the same bowl. You could, if you had a lot of time, separate them again. That's the whole idea behind a mixture. And this brings us to that big distinction. On one side, you have homogeneous mixtures. Think of salt dissolved in water. It's so perfectly mixed that it just looks like one thing. On the other side, you've got heterogeneous mixtures, like oil and water. You can very clearly see the different parts. They don't mix. But wait, there's more. We can get even more detailed. We can actually break down mixtures into three main types, and it all comes down to the size of the particles floating around inside them. So the whole story of these three types really boils down to just one thing: particle size. You've got solutions, where the particles are incredibly tiny, totally dissolved. Then you have suspensions, where the particles are big enough to see and they'll eventually sink. And then you have the weird one in the middle, colloids. Let's start with solutions. This is the most perfectly mixed, most uniform type of mixture you can get. The particles that are dissolved, we call that the solute, are so small you'll never see them, and they'll never ever settle at the bottom. Think of lemonade or seltzer water or even the air we're breathing. That's a solution of a bunch of different gases. Now let's jump to the complete opposite end of the spectrum: suspensions. The classic example is muddy water. You've got all these dirt particles just kind of hanging out, suspended in the water. But if you just let it sit for a while, what happens? Gravity takes over and all that dirt settles to the bottom. It's an unstable and obviously heterogeneous mixture. And that brings us right back to where we started, with milk. Milk is the perfect example of a colloid. It looks totally uniform, right? Homogeneous. But in reality, it's a heterogeneous mix of microscopic fat and protein particles just floating around in water. They're too small to sink, but they're just big enough to do something pretty cool with light. So that raises a really good question, doesn't it? If a saltwater solution can look perfectly clear, and some colloids can also look perfectly clear, how in the world can we tell them apart? Is there some trick to reveal those hidden particles? Well, yes, there is, and it's actually pretty cool. It's called the Tyndall effect. Here's how it works. If you shine a beam of light, like from a flashlight, through a true solution, the light just zips right through. But if you shine that same light through a colloid, like milk, or even fog, those bigger particles will scatter the light, and you can actually see the path of the beam. It's the exact same reason you can see sunbeams when a room is a little dusty. Okay, so a beam of light is our secret weapon for spotting colloids. But what about true solutions? The particles are too small to scatter light, so we can't see what's dissolved in there. How can we describe exactly what's in it? The answer is a little thing called concentration. Concentration is really just a simple ratio. It tells you how much of the stuff, the solute, is dissolved in a certain amount of the whole solution. If there's a lot of stuff dissolved, we say it's concentrated. If there's only a tiny bit, we call it dilute. Simple as that. All right, let's just do a quick calculation to see how this works. Say we've got 40 grams of salt, that's our solute, and we dissolve it in 320 grams of water, which is our solvent. The first step is to get the total mass of the final solution, so we just add them together. 40 plus 320 gives us 360 grams. Now we use the formula. You take the mass of the solute, divided by the total mass of the solution, and then just multiply by 100 to get a percentage. And boom, there's our answer, 11.1%. So what does that number actually mean? It means that for every 100 grams of that saltwater solution, 11.1 grams of it is pure salt. See? It's a super simple but really powerful way to nail down exactly what's in that mixture.
Okay, so we've pretty much established that most of the stuff around us are mixtures. But what are the mixtures themselves made of? This question actually brings us full circle, right back to where we started, with pure substances.
When you get right down to it, all matter in the universe is made of just two types of pure substances. First, you have elements. These are the absolute basic building blocks you see on the periodic table, things like iron or oxygen. Then you have compounds. That's what you get when different elements chemically bond together in a fixed ratio, like how hydrogen and oxygen bond to make water, H2O. And this right here is the biggest takeaway. In a mixture, the different ingredients are just kind of hanging out together. They keep their own individual properties, but in a compound, the elements have gone through a chemical reaction. They've become something totally new, with brand new properties, and they're always combined in a super precise fixed recipe. So let's bring this all back home. Here's a little challenge for you. Next time you're in your kitchen, take a look around. Besides maybe the sugar and the salt, how many things can you find that are truly pure substances? My guess is not many. You'll start to see that you're living in a world that's made almost entirely of these amazing, complex, and fascinating mixtures.